So I had a good question right there about ionic bonds, and it was whether ionic bonds were stronger than hydrogen bonds, and yes, they are. It's about charges. So let's just go ahead and review that really quick. So intermolecular forces, all right, and I'm going to include ionic interactions here because even though ions aren't molecules, which is why I think your book does that the way it doesn't include it in the first time it introduces it, they do count in these forces. So we've got London forces, we have dipole-dipole interactions, we have hydrogen bonds, and then we also have ionic interactions, or ionic bonds, sometimes they're called. So the way to think about these is that as these get stronger in this direction, as a consequence of getting stronger, the boiling point goes up. So if we have we would only do a boiling point for a one substance, not a combination of some things. The boiling point goes up. And the way to reason this out, what's causing all of this is the charge increases, okay? So in other words, here we have, or not in other words, more detail. London forces are very small charges and they're temporary, right? They're induced charges, they're temporary. Dipole-dipole are permanent charges. They're larger than the London forces, but they're not huge. Hydrogen bonds are even more larger partial charges. And then when we finally get to ionic interactions, now we're talking about full charges. All right, and so we get the largest interaction there. And then I don't want to spend, but you can ask me more questions about this in the quiz, and there'll be an answer key. But as we look here, when we start mixing these things, kind of look at it and think about adding up all the charges. Okay, does that make sense? So if I had a hydrogen bond interaction versus a hydrogen bond with an ion, a hydrogen bond donor with an ion, the hydrogen bond donor with the ion wins. Okay? Questions? All right. Well, let's go on. Got a bunch of stuff to talk about today. We are going to be talking about phase changes some more. Actually, let's talk about things we've got going on next week. We have a quiz on Friday. Okay, so I have a quiz next Friday. We will have there'll be a help session. And I had 5 people at the help session last night. That was great. On Thursday, on Wednesday, it's 7:30 Google Meet, the links on other things. I'll talk more about that next Wednesday, or I'll give you more detail. I do have office hours today, so and those are 1:15 to 2:15 if you want to stop by. You know, if you wanted to work some problems and things, I could help show you some stuff. We could work some problems in the hall if you want to work on the homework and then stop in and out. That works as well. And then I think that's it for us. Oh, we'll have a homework due. We have a homework due on Saturday at 11:59 p.m. And then I'm going to assign a homework today, and we'll have a homework due on Wednesday at 7 a.m. So 7 a.m. is going to be our normal time to have those things due the day of class. We don't have class on Monday because it's Martin Luther King Day. Any questions on things we're doing in the course? Okay. If you have questions on these, if the homework system has screwed you over in some way, let me know. Not right now, but let me know either by email or after class or something so I can help you work on it. Okay, so then let's go on. We're going to talk about phase changes. Not phase changes, but we're going to talk about heating curves. That's really the right term because we're going to have a phase diagram and it's something different. So heating curves. and phase changes. Okay, and we're going to, in terms of using these heating curves, we're going to today learn how to calculate how much heat's used in one of these things. Okay, so what we've got here is I've got this table here. I'm going to pull it up. We're going to look at it briefly. I'm going to put it away for a second. But so we have this table that tells us constants we need for these sorts of things, and we need all 5 of these constants. You don't need to memorize them. I will always give you the constants. Okay, if I forget, ask. You think if I said, hey, I'll give you this, and I forget on a quiz, let me know. Okay, so I can fix it. But we're going to use all those because we have 2 equations. One you've seen before that we're going to do these calculations. So if I have a heating curve, and we're talking about a heating curve for water, all the heating curves go heat on the bottom, and they go temperature over here. I'm going to do my temperature in Celsius. We're going to do water because we're familiar with it, but we could do any substance. Okay, if we were doing some other substance, these numbers would change. All right, but you'd be given those numbers. So we've got heating curves and phase changes. So if we think about water, we take some ice out of the freezer and we start heating it. It's going to get to 0 degrees Celsius where it starts to melt. And so then we would have ice, solid water, and liquid water for a while. We put in heat and the temperature would not change while we did that. Then once all of it was liquid water, then the temperature would start going up again until it got to 100 degrees and it started turning to vapor. So it started boiling. And then it would stay at 100 degrees until it was all steam, essentially. And then the temperature could go up again. All right, and so we can label the parts of this again. I'm going to label this more generally than water because it is more general than water. So we have solid there. We're going to have solid and liquid on this first line. And of course, the temperatures would change. If this was iron, right, I'm going to have a much higher temperature at which it melts and which it boils. And then here I'm going to have liquid only. And here I'm going to have liquid plus gas. And then here I'm going to have gas only. All right, we have done last semester what you did was we talked about these changes in temperature and we learned to calculate the amount of heat required to change the temperature. Okay, so we had an equation for that. That equation was Q times, we used S for specific heat capacity is what's used in your book, times, and that specific heat capacity would be the specific heat capacity for the solid or for the liquid or for the gas. And for a given substance, they're all going to be different, right? If we look down here at this table, we've got a different specific heat capacity for ice, for liquid water, and for steam. And that's going to be then times the mass we have in grams times the change in temperatures, the temperature that we're getting for a change there. And I'm going to, rather than put in change in temperature, I'm going to write temperature final minus temperature initial, which is the same thing, but we're going to be given temperatures in these problems. So it'd be good for us to have it all set up like that. This equation then, it goes for, it's only good when what's going on? When we're getting a temperature change. So it's not good for these horizontal lines, but we're going to use it here, and we're going to use it here, and we're going to use it here. Okay? The other new equation that we're going to use is this one. Well, it's not even shown, right? I'm going to give it to you right now, but we're going to be using these constants. So we've got a change in heat. This is a change in heat there, and it's a certain number of kilojoules per mole to cause us to either have, this is the heat of fusion, so this is the amount of heat that is released when something goes to solid, from liquid to solid, or it's absorbed to take it from solid to liquid. Okay, and then heat of vaporization, it's the amount of heat that's released when a gas turns to a liquid. or when it's the amount of heat that would be absorbed going from a liquid to a gas. Does that make sense? Okay. So we don't have a temperature change in that equation. It's also per mole, which like I said before, I don't like, but I can't change it. I didn't make the rules here for how they do these. And this is how it's generally presented. So I need you to be prepared for that sort of thing for other classes. But it's going to be the amount of heat is equal to this constant we read off the chart, which is the enthalpy. Remember, enthalpy is heat times the number of moles. Okay, I'm going to put this in different, I'm going to do this in orange. And so this equation is for here, and it's also for there. All right, so we have this equation we can use for various things. I'm going to give you a second or maybe a minute here to finish copying that down. You can look bored once you have it. And then I'm going to move on and we're going to do a problem.
Are the moles on the slanted lines changing or something?
The moles are not, that's a great question. Are the moles changing on the slanted lines? They're not. And moles aren't changing anywhere.
So go ahead. Could you use that formula for the whole, the realignment?
Okay, that's a great question as well. Could I use this formula for these lines? What's going on here that isn't going on here? The temperature is changing, and you need to use the formula that has the different temperatures for the slanted lines. Does that make sense?
I was getting confused with the heat and temperature part of it, but yeah, that makes sense.
Yeah. Okay, so let's go on and let's try working a problem for this. And these are the sorts of problems we'd ask. But essentially what we're going to do is if we have a change in temperature, we're going to have a change in temperature. It's going to go from ice, we're going to melt it, and we're going to raise the temperature a certain amount. We could actually go from ice and go all the way to gas. There's even more complicated questions. I'll show you one from your book. I don't know that we're going to go there, but we could do that as well. But what we've got here is, so if we go from, we're going to have an example here where we go from ice to liquid water at a certain temperature, and so we have to calculate that heat change using one equation. We add this heat change to it from another equation, and then we use the equation again to figure out what this heat change is, and we add them all together. And that's what our process is going to be here. So let's go ahead. We're not going to do that problem. I'm going to try to do the same problem I did for the class earlier, since I'm going to post this. So if I have 15.0 grams of ice at negative 2.5 degrees Celsius, and I heat it to 64.0 degrees Celsius, how much heat was required? For this change? All right, so the first thing I want to do is I want to give you a minute or maybe two. I want you to draw me the heating curve for this. So this is a thing where I did the temperature versus heat. Show me where you start, draw your slanted lines and your horizontal lines you need to do that. And if you get done in your board, go ahead and write out what the equations are for each. Okay, without the constants, the general equations, and point them to where they go. Yes?
Do you want a whole, phase change heating curve for water, or just up into the temperature?
I would like you to, that's a good question. I would like you to draw me just this.
Okay.
Heat curve that just includes these changes. Okay, I see that some people have that. Let's go ahead and talk about it. So I'm gonna go ahead, I'm gonna start just by doing heat. Heat's going in that direction, and then I've got temperature over here. We're doing water once again, so 100 degrees and 0 degrees are helpful. Where do I start? Negative 2.5 or below 0, right? So I'm going to start down here and I do a slanty or a horizontal line? A slanty line, right? Until I get up to 0, and then it's going to go horizontal for a while, and then it's going to go up to where? Go up to 64 degrees. So this is 64 degrees Celsius. Okay. Put all my significant figures in here. And this is negative 2.5 degrees Celsius. All right, in terms of my equations, I'm going to have an equation that looks like this. We'll go ahead and do all of our equations here, and we'll actually go ahead and put the numbers in. So my general equation for this top slanty line, I'm going to do that one first, looks like this. Okay, that's the general equation. And then to make it specific, I need the specific heat capacity of water. So I'm going to go look at my table. For liquid water, which is the slanty part of the curve we're on, it's 4.184 joules per gram Celsius. So this is going to be 4.184 joules per gram degree Celsius times the mass, which was 15.0 grams, right? Times the change in temperature. So that's the temperature final. What's my final temperature? 64 degrees Celsius. And what's my initial temperature for that slanty line? 0 degrees Celsius. These are pros. Okay, great. So that is the heat change for there. All right, since it's the same equation, let's do the heat change for the bottom slanty line. So that's going to be the heat is equal to the specific heat capacity, once again, times the, I didn't need to draw this again, I should have just put the numbers in, but there we go. And then if I go up here and look at it, what's our phase of matter down here? Solid, right. So let's go up and look for solid. For solid, do you see it's 2.02? So 2.02 joules per gram degree Celsius times 15.0 grams. And then what's our final temperature for that slanty line on the bottom? Okay, negative 2.5 is our starting temperature, right? 0 is where we end up, right? We think about going across. So, and then I'm going to minus 2.5 degrees Celsius. Now, minus times a minus is a plus, right? Or minus, well, it is a minus times a minus, is a plus, and so that'll make my signs work out correctly. All right, one more to do here. This is going to be, now we need to do this horizontal line right there. This goes down here. Okay, so now we do the horizontal line, and that's going to be our enthalpy change times the number of moles we have. Okay, great. Now I've got to convert that, if I'm going to do that, I need to figure out how many moles I have. But I have 15 grams of water. So if I have 15 grams of water, how do I convert that to moles? I'm going to use the molar mass. Okay. Does anybody accidentally memorize the molar mass for water yet? 18.02. Okay, great. You guys, great. So if I 18.02 grams of water, that's 1 mole of water, right? Why did I put the grams of water on the bottom? Yeah, to cancel, right? We're going to cancel like that.
How many decimal points do you want us to have the stuff with the periodic table?
I would go the question is, how many decimal points do I want you to use off the periodic table? I want you to go at least 2 decimal points out, okay? So we're not limiting things by significant figures. Also, most of you haven't had me for a course before. In terms of significant figures, I just want you to be close. So I don't want you to give me every number out of your calculator. I don't want to get a single significant figure unless it's valid based on the question. I don't want you to spend a lot of time thinking about significant figures. I want you to be thinking about, in this case, heating curves, okay, and how to do the calculations. So, so those two things will cancel, and if I just do that in my head, no, I just memorized it from last time. I think that's 0.3832. You can correct me on that, moles. Okay, another thing I accidentally memorized, but I will have forgotten that one by next week. All right, so what we need to do here then is we're going to put that up. Well, actually, I do need my chart. The chart, where's the chart go? The heat of fusion, right? We've got something melting or we have something freezing, so we're going to use the heat of fusion. That's 6.01 degrees. And is it absorbed or is it, so for this process, are we absorbing heat or are we releasing heat? We're absorbing heat, so it's going to be positive. Remember, when you absorb energy, it's positive, and when energy is released, it's negative. So we need that to be positive, 6.01, and that was kilojoules per mole. And then we had 0.832 moles. All right, and so that's going to cancel with that. And we're going to end up with an answer in kilojoules. Is that going to cause us problems when we need to add these together? Yeah, so let's fix that, but we'll fix it in a minute. Let's go ahead and just calculate all our answers first. So this is going to be a little messy, but I think I still want it to be that way. I'm going to go ahead and I'm going to write over these arrows. Actually, yeah, I'll write over the arrows for now. See how bad it looks. Okay, so this top one, I'm going to put in my calculator. I'm going to start, in terms of my calculator, I could do order of operations on my calculator using parentheses, or I could just do my subtraction first and do my multiplication. It'll all work out. I'm going to start over here. 64 minus 0 is 64 times 15 times 4.184. And what I get out of that is 417. What was this? And my answer is in joules because grams cancels with grams and Celsius cancels with the Celsius. Okay? Questions? All right, so then my next one is what I've got. 0 minus 2.5 equals times 15 times 2.02. And that's going to give me 76.0, essentially. 76 joules. Okay, I'm not going to worry about more significant figures there. I guess I have 3 significant figures. So it could be 75.6. Or 75.8, actually. Sorry. Joules. Okay. And then down here, I'm going to end up with some number of kilojoules. If I multiply all that together, I end up with 5.000 kilojoules. I should jump in if you get different numbers than me. Okay. So now if I'm going to add them together, I need to get them all in the same units, right? So I'm going to want to convert either joules to kilojoules or kilojoules to joules. If I do kilojoules to joules, I only need to do it once versus twice, so I'm going to do that one. So if we come down here, we say 5.00 kilojoules. What do I need to do to convert that to joules? Okay, multiply it by 1,000. There are 1,000 joules in a kilojoule, right? So multiply by 1,000 is correct, but the way I would double check that, let's say I was really tired or something and doing this sort of stuff, I didn't want to make a mistake, is that I need to make sure my units cancel, right? So there are 1,000 joules in a kilojoule. Kilojoules cancels with kilojoules. That's what tells me that I multiply as opposed to I divide. And so I'm going to end up with 5,000 dot joules. All right, so I'm going to go ahead and I'm going to add that up here. I am going to go ahead and erase these lines just to make a little more room. And that's going to be 5,000 joules. So now I just need to add those all up. So take that down here, and
Don't you have to divide by the molecular mass? Because doesn't it have to be in joules per gram like the other ones, not joules per mole?
all I need is joules. So what we had, so it's a good question. So we had our grams, right? We figured out how many moles were in those grams. And so we know it doesn't matter. This is not joules per mole anymore because the moles cancel. So that it's just joules, or it was kilojoules and made it into joules. But the grams went into this. Remember, we had 15 grams made that many moles.
Oh, the unit of enthalpy is, sorry.
Yes,
I missed
yes.
that.
Nope, that's confusing. And as I've said before, I wish they hadn't done it that way. I'm just going to go ahead and round this to 76 now. Okay, because I'm gonna lose that sig fig in rounding anyway. And then joules. And so if I add these up, I get 9,093 joules for that change. Other people get that? Okay, I'm seeing some nodding yes, so I'm going to assume that that's correct. Questions on that process? Okay. So we may come back to it as a problem. These problems can get more complex than that. Here is a more complex problem from your book. So this is a great problem. What they've done here is they're dropping a chromium block at 400 degrees Celsius. It's got a lot of heat in that thing, into some water. And the water is going to go to boiling, it says. And some of the water is going to actually turn into steam. It's going to turn to gas and go away. And what they want you to do is calculate how much of that water would have actually evaporated. All right, so we can use that same sort of process we did there to solve this problem. And this is one out of your book, and it's an example in the book. We're not going to do it right now, but I want you to see that these are the sorts of things we would do, right? You can do lots of stuff with that heating curve. And essentially what you'd be seeing, you'd be figuring out is how far, if we were to draw our heating curve, this one starts at 20 degrees Celsius for water. So this curve is going to start here, and it's going to go somewhere into here, and we're going to solve for that. So you could do that sort of problem with these, and there will be homework. And then another thing is we might not be doing water, in which case all of these constants change. So this is carbon disulfide. All right, so if we have carbon disulfide, then we have different melting points and boiling points, and we have different specific heats and different enthalpies of vaporization and fusion. Okay, so it's not always going to be those same constants. For now, we're going to go on, though, and rather than work another problem on that, we're going to go and we're going to move on and talk about phase diagrams. And then if we have time at the end, we might come back and work another problem. Okay, phase diagrams are essentially the graphs that help tell us what phase of matter a substance is in. And at a given, they're related to temperature, right? We've talked about phases in regards to temperature, but pressure matters too. So what phase a substance is in at a given pressure and temperature. So here we have a phase diagram for water. And it shows us that water has it has its three various phases, include another phase that we'll just kind of briefly describe, but not spend a lot of time on here. So under these conditions, under these sets of pressures and temperatures, we have water as a solid, then it can become a liquid as we raise the temperature, or depending on low pressure, we can have water go directly from being a solid to a gas. Okay. What we're used to is 1 atmosphere pressure. That's where we live. And we're used to water going from a solid to a liquid, and then it becomes a gas. Okay, that's how we're going to read one of these, and we'll talk a little bit more about that sort of stuff. But there are some interesting other things here. So the triple point is shown right here, and the triple point is the combination of pressure and temperature where water is a solid, a liquid, and a gas all at the same time. So it's like when we think about the melting temperature of water. When we think about water melting, right, you can have water that is liquid and water that is ice all at 0 degrees at 1 atmosphere temperature. You can both in your drink at the same time. If we were at this lower pressure, I don't know what that pressure is actually, but if we were at this lower, and they say this isn't the scale, but we were at a lower pressure, we can actually get, instead of we can all have water sitting around as a gas, as a solid, and as a liquid all at that same time. Okay? Does that make sense? Let's go ahead and define the triple point. So the triple point is the specific, so it's a point, right? It's not a line. The specific pressure and temperature where a substance exists as a liquid or can exist as a liquid, a solid, and a gas at the same time. Okay? All right, let's talk about the critical point. The critical point is a pressure and temperature above which a substance acts as a supercritical liquid, supercritical fluid. Okay, and let's talk about what a supercritical liquid is. A supercritical liquid is a phase where a substance acts as both a gas and a liquid. So it's interesting. Okay. So you're not going to see supercritical fluids very much because they happen really kind of at high pressures and higher temperatures. I'm not sure of a use for supercritical water, although I bet there are lots of them. Okay, I don't know one to talk to you about. But you guys familiar with dry cleaning? It's like if you have some clothing and it's really sensitive and you don't want to put it through the washer because it's going to mess it up. It's going to cause it to degrade or become apart, sort of, or it gets roughed up. Think about it gets roughed up really fast, let's say. Well, for carbon dioxide, we have a critical point, just like we have a critical point for lots of things. But at the critical point, you get this supercritical fluid, and supercritical carbon dioxide gets for things like dry cleaning, okay, It also gets used for things like decaffeinating coffee. You take this supercritical fluid and you run it over the beans and that takes the caffeine out, okay? And it's better than, it's preferred over doing things like using dichloromethane. So the way these things often got done, or that used to get done, both dry cleaning and decaffeinating coffee, having problems getting the right thing here, okay, is used to use dichloromethane, and dichloromethane looks like this. Actually, that's not right. One of these has to go back. Dichloromethane looks like that, and you may not have a feeling for this, but you don't really want to be ingesting for your coffee. If there's any residual dichloromethane around, you don't really want to be ingesting that. Okay, not things with a lot of chlorine on them are not good for you in terms of organic compounds. Sodium chloride has chloride in it. Chloride's just fine. But these sorts of compounds aren't good for you. They're also not very good for the environment. All right, so even if they get all of it out, if it goes up into the air, compounds like this are really great at destroying the ozone layer. Anybody know what the ozone layer is? What's the ozone layer do for us? Yeah, it blocks UV radiation. It keeps us from getting sunburned, right? And then skin cancer. So ozone layer is really important, need to preserve it. And so one way to do that is to use carbon dioxide, supercritical carbon dioxide, to do things like decaffeinate coffee instead of using dichloromethane. So let's go back up and take a look at, let's talk a little bit more about this phase diagram for water, okay? And let's talk about cooking, all right? So cooking, sometimes if you want to cook things faster, what can you do? Let's say I want to make rice and I want to make it fast. I don't want to wait for it. Or I want to cook beans and I want them in 10 minutes or 15 minutes. I don't want them in 2 hours. I don't know if you guys ever do dried beans, but you know how we do that? Yeah, use a pressure cooker, exactly. Okay, so you could use a pressure cooker. Now remember, these axes aren't to scale, which means they're not linear. Okay, so let's say I'm going to go ahead and put this on here because I know what this temperature is. But anybody know what pressure a pressure cooker cooks at? So we live at 1 atmospheric pressure. What's going on in that pressure cooker? It's about 2 atmospheres. Okay, so if we think about 2 atmospheres, let's say 2 atmospheres is here on this plot. And we follow it over. Why does a pressure cooker cook things faster? Anybody know? The answer is not because you're using pressure, although it... What was that?
The relationship is proportional.
What relationship?
The relationship between pressure and heat. Between
pressure and temperature, right? Okay. So what happens is you're at 2 atmospheres of pressure, and that puts you at about 120 degrees Celsius. So you are cooking, if I'm trying to get my rice done faster, I'm trying to get my beans done faster, I'm cooking at 120 degrees Celsius instead of 100 degrees Celsius, and things happen lots faster because it's hotter. Why, if I have my lid open on my beans and they're boiling, why can't I get that temperature above 100 degrees?
Because it's in equilibrium with its surroundings, so all the heat is being released into the air.
Okay, we're getting heat released to the air as it boils off, but what I'm looking for is, I agree with that answer, but what I'm looking for is an answer that uses this. If I'm boiling beans, what temperature are those beans at? They're at 100 degrees Celsius, because until all that liquid is gone, my beans can't get above 100 degrees Celsius. Okay, so that's where the pressure cooker helps. If you put pressure on there, you can get the temperature higher. Okay, once all the water boils off, those beans can get hotter than 100 degrees Celsius, but you don't want to do that if you don't already know that. That tends to smoke up the house. All right. Questions? You see how the pressure and temperature stuff is interesting and useful? Okay, if you and anybody ever live in like Denver or someplace at higher elevation than us and try to do cooking? Okay, well, if you live at a higher elevation than us, what happens to your pressure? We're actually really not at 1 atmosphere of pressure here because we're not at sea level, right? But it decreases, right? So you'd be down here, and so if you're cooking in Denver, you have a lower temperature that things are going to boil at, water boils at. And so it isn't as hot when you cook things that involve boiling. And so you need to actually cook things longer, okay? It's not, I don't think it's 90 degrees, but it might be like 96 degrees or something like that. Questions? Yes? Yes, it's at higher elevation, the air is thinner. So when we think about pressure, what air pressure is the molecules in the air bouncing off of stuff. So they're bouncing off of you, they're bouncing off of everything, really. They're bouncing around. And if you have less air, you have less pressure because you have fewer molecules bouncing off of things.
That's why it's so high, like underwater.
That's why it's high underwater, is because you actually have the pressure of, it's the atmosphere and it's the water, but it's also the water is more dense, right? If you think about the pressure we're under, you can think about it as molecules bouncing off of stuff, but you can also think about it as the column of air that's above you, right? So if you were to go deep underground, presumably you would also be under even higher pressure because you have a greater column of air above you, pushing that air down. Okay, so let's go ahead. Didn't realize I've almost used all my time here. I was having a lot of fun. I lost track of time. So let's make sure, let's try a problem here, and then we'll be done. Okay, so here's a problem. This involves benzene. And what I would like you to do is, let's go ahead. I would like you to take this phase diagram and let's answer the question. What it wants you to do is, using the phase diagram below, estimate the melting and boiling point of benzene. Let's do the first one at 0.05 atmospheres. Go ahead, make an estimate of that. Write that down. I'm going to give you 30 seconds, and then we'll answer it. We'll look at it together. Okay, what do you guys think? What's a good estimate for the melting point of benzene at 0.05 atmospheres pressure? About what? Like 5.7, right? That's a pretty good estimate. Okay, so if we follow this over at about 0.5, maybe it's 0.57, maybe it's still 0.56, right? Degrees Celsius. Okay. How about the boiling point? Somebody else. Where would you estimate that roughly? Just 10? Okay. So we follow this over, we follow it down. Yeah, maybe that's 10. It's probably not, it's not the scale anyway, right? But 10 degrees Celsius. You see how you read one of these? So if you're given a temperature and you want to know what pressure something happens, you follow the temperature up. But here we were given a pressure, we wanted to figure out what temperatures things happen. So we took the pressure, we followed it over, and then followed it down. Does that make sense? Okay. All right, you guys have a good, I'm not going to get to see you again for 5 days. You guys have fun. Look for homework, okay?